Okay, so we're going to move on to the new chapter, which is talk about the carbohydrates. So that will be carbohydrate number 1. So first of all, carbohydrate, what this means, when you look at the word, looks like carbo and then say hydrate, that means it's C and H2O. So carbo is a water, and then we write M or we write N. And we can say M could be equals N, or N could be unequal with N. That means multiple molecule of carbon and water combined become a carbohydrate. Now carbohydrate has another name coming from a Greek word, S-A-K-K-H-A. I don't know how to pronounce, but in English we call it a saccharide. Therefore, it comes with a very important 3 different categories. Number 1, we say monosaccharides. This is everybody knows, like glucose, like mannose. There's a lot, we will talk about that. Then second, it's ideally we'd say disaccharides, but we usually say oligosaccharides. So what are the examples? Let's say sucrose. Let's say lactose. Those are oligosaccharides. We'll have a section to talk about that. Now last one, obviously, is polysaccharides. So for example, when we talk about starch, is a good example of polysaccharides. Now, when we talk about the polysaccharides, we also categorize it into digestible and undigestible. So for example, like starch is digestible. However, there is another one, let's say chitin and cellulose. Cellulose basically is making like a coat. Those we call it undigestible. So our lecture will be based on these, talk about each category. So today we're going to first talk about monosaccharides. Now before that, we want to mention is we talk about the DNA all the time. That's called enantiomer. So we talk about the D configuration, we talk about the L configuration, that's called enantiomer. And in our nature, most of the products picks D configuration. L configuration, very few existing in our natural life. It is most likely present as a components in polysaccharides. So these are the opening remarks. What is a carbohydrate? We're going to talk. Then we move on to talk about the details. And I said we're going to focus on monosaccharides today, so we want to focus on monosaccharides. Okay, the first question. What is the simplest sugar? If you can think about it, the simplest sugar, it's very similar to the components we talk about in our second lecture when we go over the biochemistry cycle, if you still remember. CHO, CHOH, CH2OH. That's the simplest sugar, which is what we call it glyceraldehyde. And then I can write another one, CH2OH. CO, carbonyl group, then you have a CH2OH. This guy looks very similar. Okay, we talked about before. Dihydroxyacetone. Do you familiar with that? When we talk about glycolysis, if we add a phosphate there, what's that? Glyceraldehyde 3-phosphate. If we are adding a phosphate there, dihydroxyacetone phosphate started as a branch reaction of the glycolysis, and we also say this is reversible. So this gives you a 2 example. If we remove the phosphate, okay, the 2 example of the simplest monosaccharides. This one, only 3 carbon, but very typical. You have the guy here. You should write like this. What's the name of this structure? Aldehyde. So how we call this one? Aldose. The second one, dihydroxyacetone phosphates. You see here, this guy at the middle. This is a ketone. So how we say? This is ketose. The same chemical structure, same 3 carbon, the same 3 carbon monosaccharides, but looks like the structure is completely different. We come out with our first isomers. We're going to talk lots of the isomers. And this one we talk about is constitutional isomer, which means it's completely different. You can understand. Okay, now we're gonna talk about is a long list. Okay, so let's do a good example how we gonna draw it. Okay, I'm gonna draw right in the middle. If I need a space, we can use a space here. So, in the chemistry, there is a family tree talk about aldose. I'll use aldose as an example. Ketose, we're gonna skip it. We don't have that much time. So what happened? We using O to start with this. I can even draw bigger. Don't have to be that small. So, looks like a figure, okay, cartoon figure, but we can label it. This means CHO. That's aldo. That's aldehyde. This is a carbon line. What this means is where the OH goes. Okay, that line means OH goes. What's the bottom line? The box represents CH2OH. So we're going to do the family tree. Okay, let's draw the first one at the very top. What we call this? 3 carbon. So we say this is 3 carbon. Trials. We call it trials. Now obviously we already know that's glyceraldehyde. Glyceraldehyde. Okay, now we're going to start a family tree. Goes here. We're going to add the carbon there. Is it the same? We can add 1. Draw it a little better. At the right. We also can add 1 at the left. That's D, that's L. Okay, what is this called? Obviously, this is 4 carbon. What we call it? Tetrose. That means 4 carbon. What's the name of this one? Erythritose. What's the name of that one? Cereals. Okay, that's 4 carbon. Now, let's go to do 5 carbon. Okay, 5 carbon, it's going to be a little bit long, but lots of fun. Okay, we're going to do this. Right. Okay, that's aerosols. We're going to add 1 on the right, add 1 on the left. What is this one? Everybody knows it. You just didn't realize it. That's ribose. What's a ribose for? DNA or ONA. Okay, what is that one? Everybody also knows. Everybody knows. Remember, we talk in the genetic class, we have a lacto-operon, we have an arabinose operon, which is a dual channel, a circle. That's arabinose. Okay, cereals, what we're going to have? Let's just draw the same, okay? That's a little long. 1 on the right. This. Go here, draw this. This one goes here. This guy on the right, this guy on the left. What is this one? I bet you heard about it. Exolose. XLT4, agar, everybody knows, for salmonella. growing. What is this X? Xylose. That's a 5-carbon sugar. What is this one? Lysine. Remember, long CH2, epsilon amino acids. What is that one? 2-GTO4 are selective ingredients. That's where the xylose come from. What is this one? Lysose. Okay, 5-carbon, you know. What's the name for that? We call pentose. Remember pentose phosphate pathway? We talk about in our biochemistry class. Okay, now let's go. 6-carbon. That's a little challenge to draw, but we're gonna do it. Okay, how we do? Go here, we go. Right here. Okay, that's the same. Little here, okay. Little bit on here. So otherwise not much space. Okay, let's do. Add one on the right, add one on the left. What is this guy? That's not many people know. Aros. What is this guy? Ultros. Need to make sure I'm doing right. Okay, Aros and Ultros. Not many people know. This second one. This is a big deal. Okay. So this one right here. We go here. This already finished. So we go here. One on the right, one on the left. What is this guy? Everybody knows. Glucose. Let me write it clear. Glucose. What is this guy? We just talked, the mannose. Okay, not done yet. Let's go talk about here. Let's go here. This line goes here. We'll have, we call it xylose goes here, okay? Yeah. Left, right. Right, left. What is that one? That one, not many people know. Glucose. And this guy, not many people know. Idose. Okay, last one. Go here. Left, left, right. Go here. Left, left, right. Right and left. Sorry. What's that one? Lots of people knows. Galactose. What is that one? Nobody knows. Tyrose. That's a family tree of monosaccharides of aldose. Okay, that's 6 carbon. What we said? Hexose. So it's very lots of fun when we do this. And you know all this structure, you just added it. This OHC, COH, COH. Okay, now what we want to say. When we talk about triose, tetrose, pentose, and hexose, this is aldose. Okay, if it's ketose, how are we going to say it? 3 carbon ketose is TRIULOSE. Triurose. Tetrose, if it's 4 carbon ketose, called TETRULOSE. That's tetrose. Pentose, if it's ketose, what we call it? PENT. We add ULTOSE. Pentatose, the last one, that's 5 carbon. The last one, 6 carbon. Hexose. So what's it is? Did you see the same? Is only the middle add UL. That means here is ketose. Here is aldose. Now for the ketose, of course, you have another family tree. We just doesn't talk that too much because in the for the microbiology, for the chemistry or for the science, we doesn't talk that too much. Something usable, something not usable, or completely chemistry. That's another discipline. Here we want to say something. Glucose and mannose, what's the difference? Exactly the same. The only difference, carbon number 2. Okay, then look at it one more time. Glucose and galactose looks exactly the same. What's the difference? Is carbon number 4. This comes out with a second, or actually third isomerization. We're going to mention. The only difference is the position, carbon 2, carbon 4, make the difference, we call epimer. Okay, we'll do a conclusion later on when we finish, because this is important. So that's a family tree. We already talked about N and T-imer, constitutional isomer, and epimer. Those are the 3 major isomers. Have not done yet. Now, we want to spending time talking this guy. Obviously, glucose is most important. So we're going to talk about the glucose. Okay, that's will be the key thing here. So glucose. Let's go ahead and draw the structure. You already have it. So you know how to do glucose. CHO. If you draw here, there will be HOH, COH, H. The others are the same. HOH, OH, CH2, OH. Okay, this is glucose. We want to mention several things. 6 carbon. Let me write the glucose first. 6 carbon. There's no question. We want to first say carbon number 2, carbon number 3, carbon number 4, and carbon number 5 are important. Because 2, 3, 4, 5, we call 4 chiral carbon. Which means every carbon there is a center, is a geometrical center when we talk about organic chemistry. Okay, what is the name for this chemical structure that everybody heard about before, even you don't know? That's called Fischer projection. Okay, where is Fischer projection comes from? This we need to go back to talk about we learned in lipids section. If you remember, we have a center right here. That could be like this, or could be like that. This will be completely filled like you are going back to the airport. And then you hear the perpendicular when you have something like this. And then you have something like that. Like you flee away from the airport. This is called a slash. Now how the Fischer projection of the chemistry comes from? They are looking for the imagination of you have the eye. Go, this is your eye, let's say. 45-degree angle. What it looks like. That's called the Fischer projection. So glucose could write different formation, and this is the first one. Fischer projection. That's a very old time people doing that. Okay, now we know later on with organic chemistry development, they thought about the other way to express, because Fischer projection, you cannot see the spatial view. It looks like a line. We say 3-dimensional, this is the 1-dimensional. Only you know the chemistry, the chemical numbers, you don't know the configuration really. So, they come out with a different structure, which is this guy. Turn 90 degree. Then becomes what? When a structure everybody knows. Looks like that. But there is some story behind it, okay? This Fischer projection, you simply turn 90 degree, what is it going to be looks like? See? That's no problem, okay? H, OH, no problem. OH, H, then you go here, OH, H, then you go here, OH, H, CH2, OH. That's what it originally looks like. Okay. That's the first different configuration comes out. Then people are gonna be doing a projection. What this one end up? There is a story behind it. When you start from here, there are 2 different scenarios will happen. So number 1, what will looks like? I do it simple. this will look like. Okay, what's the problem? What's the issue? This looks like that, this becomes that. If you count 1, 2, 3, 4, 5, 6, and 7. This is called 7-carbon ring. Unfortunately, our nature rejected because thermodynamic unstable. So we don't have 7-carbon ring. If you don't remember this, go to the casino, have a game called Grabs. You go Three River Casino at Pittsburgh or Los Angeles, there's the crabs. So throw the dice. What happened? 7 showing up. The host take all money on the table. It's the same thing. When the 7 comes, everything is gone. The nature doesn't accept the 7-carbon ring. It's a joke, just to let you to remember. We don't exist in that one. Okay, so how they do? So the chemistry person gonna work on that one, okay? How they do? They think this way doesn't work. They're gonna make a turn. Okay, once this make a turn, what happened? That's really magic. Once this make a turn, you can imagine on your mind what it will be looks like. If that looks like this, these are the same. H, OH, no difference. OH, H, H, OH. So you go here. What's there? That's O, that's H. What's the magic before you make the turn? The rotation brings O forward. Or we say upward. Okay, then they can react it. That's very lucky. Something could react it. Why they can react it? Now we're going to go back. What's a sublayer orbital? That's why I need to talk the situation. Otherwise, it's confusing. 1s, 2s, 2p. What's oxygen looks like? Up, down, up, down, up, 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 go down. What's a carbon looks like? Very similar. That's 2p layer. Go here. Then you go up, down, up, down. That's Pauli exclusion policy. Then hands loose. That can be reacted. Octet rules. So later on, what it becomes? Moves here. That comes out. with a very standard configuration comes out. OH, H, OH, OH, H, OH, H. What's that one names? Hayward's configuration. What is a good advantage for Hayward's configuration? Look at this carbon in here. That is a chiral center. We call anomeric carbon. So, how many carbon center? The carbon C in the Fisher projection, it is 4. Then, how many chiral carbon in the Hayward's configuration? It's 1, 2, 3, 4, 5. This one is not. Okay, what this means? From Fisher projection to Hayward's configuration, they are adding 1 carbon chiral center. Make it thermodynamically stable. It's very important. It's a breakdown in the chemistry history. The person is Harold, I believe. The name is by, let me see who created this. Okay, sorry. I forgot about that. Who created this configuration, this theory about it, okay? Now we know. This is called semi-acyl. This is also comes from a semi-acyl. Sorry, hemiacyl. Okay, comes from hemiacyl, which means it's a typical example. It's a reducing sugar related to that. So we can say it's contribute to reducing sugar. So this is we talk about Hayward's configuration. Hayward's configuration. The advantage can be seen by spatial view. That is important. It looks like you can see a space set of view there. The spatial view there. Okay, now people want to develop something else. So we said this is 1, this will be 2. People find it's not enough. We can see the chemical structure, we can see the spatial view, however, we cannot see the angle of the ring. That's very important. What are those ring called? 5 carbon, pine nose ring. So, honestly, what is glucose we really call is D-glucopyranose. If we really want to give a full name, this is called D-glucopyranose. That's its full name because it becomes a pyranose ring. But we want to see the angle of the ring, so what becomes? This comes with last structure. I always didn't draw this one very well. I'll try. What this one called? This is a key. That's called chair configuration. Can see the angle of the ring. You see the angle of the ring? Now, what comes out? This comes out with something interesting. Think about the 3 dimensions in your mind. Perpendicular, axial position. Horizontally, equatorial position. This gives you, if we put everything simple, everything concisely, this comes out with, let's just draw this briefly. If this OH goes this way, on the top, this is called beta. And if goes to the bottom, it should be straight, okay? If this goes to the bottom, which is, if it's a equatorial, it's beta. If it's axial, that's alpha. This is called anomer. And the research has been showing our nature prefer beta anomer. So 64% the chance you're showing you beta and anomer compared to 36% of the chance showing you alpha anomer. Okay, here we're going to do a little conclusion. Then we go next topic. What's the conclusion here? We already talked about the isomer. So, what are the categories we're talking right now? Number 1, you have aldose versus ketose. This is pretty huge, and it basically change the structure of the isomer completely. Constitutional isomer. The second thing is you basically change the carbon number 2 with or carbon number 4. But all the else is the same. This comes out with epimer. Number 3, we mentioned about the D configuration versus Al configuration. And our nature prefers D, the Al only in polysaccharides. This is called enantiomer. The last one we just mentioned is beta configuration versus alpha configuration. That is called anomer. So when you talk about the isomers of carbohydrates, even the sugar, they have 4 major different isomers. This comes out our next topic. A terminology. Folks talk about isomers. motor rotation. MU, motor rotation. That's a terminology. Okay, what is this terminology? Means. This is a very interesting phenomenon. The chemists find it. You dissolve a crystal of sugar, or sugar crystal. Now, of course, it's a reducing sugar, okay? Dissolve a crystal sugar in water will reach an equilibrium status. Equilibrium status with mixture of isomers. And they come out with a very important formula, and the formula is K 25 degrees Celsius equal 0.0096 plus 0.250 the concentration of proton, and add 9.756 the concentration of a hydroxy. Now, where is that K25 means? 25 degrees Celsius means that is a transition kinetic parameter between alpha D, glucopyranose, in the transition step to beta D, glucopyranose.